All right, good afternoon, and thank you for joining us for the virtual ninth annual Forensic Science Symposium Lunch and Learn poster session, hosted by the Global Forensic and Justice Center. Please use the chat feature to ask your questions, and any unanswered questions due to time constraints will be provided in written format shortly. And with those housekeeping items out of the way, here's Sarah Schwing with her presentation.
Awesome. Thank you so much. All right. Hi, everyone. Thank you for joining me for my presentation today. I'm going to be talking about the precision of morphoscopic data from 3D surface scans. So essentially what I did for this research was look at the utility of morphoscopic methods that we use on dry bone in forensic anthropology and apply these methods to virtual remains. And I wanted to see if I was getting consistent scores, if it was possible to get consistent scores from these virtual remains or 3D surface scans rather than physical remains. So if I, as a forensic anthropologist, don't have access to physical remains, can I instead use virtual remains? If law enforcement or a medical examiner have access to a 3D scanner, if they can scan the remains and send them to me, I can begin to build a biological profile using those virtual remains. So to test this method, I looked at a sample of 50 mandibles from the William M. Bass donated skeletal collection housed here at the University of Tennessee. So what I did was observe 7 different morphoscopic traits, and morphoscopic traits basically mean that we are eyeballing those traits and not measuring them with a specialized ruler or measuring device. So rather I'm scoring these various traits that you can see down here in figure 1 using my eyes and a guide of illustrations. So the 7 traits that I looked at are height of the coronoid process, shape of the mandibular notch, pinching of the ascending ramus, undulation of the inferior border, protrusion of the mental eminence, gonial eversion, and shape of the inferior border. So these 7 traits are used for both sex and ancestry estimation for the mandible. So what I did was scored all 50 mandibles virtually after creating 3D surface scans using a next-engine laser scanner. And then about a week later, scored those same 50 dry elements. And for statistical analyses, I used Cohen's kappa and compared the agreement between all of those scores. So up here in table 2, we can see the results between agreement, or the results of agreement between my scores for 3D remains and my scores for physical remains. So that second column in table 2, entitled kappa value, those are the kappa values for that first test between physical and dry bones, or between dry bones and virtual bones. So in a nutshell, higher kappa values kind of indicate greater agreement, and lower values indicate less agreement. So those values that are indicated with a star, those are all significant kappa values. So almost all of my traits showed significant agreement between virtual scores and dry bone scores. However, protrusion of the mental eminence, that last trait did not display significance and had a very low kappa value. And shape of the inferior border actually showed the greatest agreement, indicating substantial agreement with a kappa value of 0.638. So that was really interesting to see this variation, that some traits showed significant agreement and some next to no agreement, basically. So after running Cohen's kappa for those for that comparison of dry bone and virtual bone, I ran the same scores through Spearman's rank correlation coefficient. And these results can be seen in Table 3. So pretty similar to the kappa values that we just took a look at in Table 2 in that second column. Spearman's correlation showed significant results for all but one trait. And again, that trait was protrusion of mental eminence with a very low correlation score. After this Spearman's rank correlation coefficient, I went back and scored a random subsample of 25 3D surface scans, just to get an idea of my consistency between scans. So what I looked at for that first comparison was consistency between dry bone and between scans. So how am I scoring bones in these different formats? And this second test, where I scored a subset of 25 scans and compared them to the scans that I had taken the first time, was to get an idea as to my consistency in scoring scans. So it's important not only to be consistent in the way that you're scoring physical bones and virtual bones, but you also want to be consistent in the way that you're scoring virtual bones from individual to individual, or from skeletal element to skeletal element. So that's what I was taking a look at for this second round of scoring. So I scored a subset of 25 scans, and again ran Cohen's kappa. And those values can be seen in the rightmost column in Table 2, and that column is entitled Intra-Rater Reliability. And what was really interesting for these results was that the greatest agreement that I saw in the first test of kappa values, so shape of inferior border and gonal eversion, those were my two traits that exhibited the greatest agreement. Interestingly, in this second round of scoring, those are the two traits that exhibited the least agreement. So there's definitely a little bit of research that needs to continue here, just to kind of tease out what these issues are. But there were a number of traits that exhibited moderate agreement, and most of them did exhibit significant statistical significance. So this research is definitely promising for the use of virtual remains in place of physical remains. But before these methods can be employed in actual forensic investigations, more research needs to be conducted, more skeletal elements need to be looked at. And of course, larger sample sizes will definitely help to provide more information as to whether or not these methods are really useful and can be implemented, or if they are not reliable simply because it's too difficult to try to interpret these morphoscopic traits on a computer. Even though you're able to rotate and manipulate this object on your computer just like you would a physical bone, it just perhaps the coloring or the lack of light or the contrast in grayscales, if you're looking at an element just in this gray color, might obscure some of these traits and make them a little bit more difficult to read on the computer versus in person. All right, so any questions?
Just want to remind everybody, if you guys have any questions, just put them in the chat and we'll lay them to Sarah. Sarah, what are some of the advantages of 3D surface scans?
That's a great question. So some research has actually been done on precision of virtual methods, which is what I'm calling this type of method. It's virtual rather than physical. However, a lot of these studies on virtual methods have used CT scans or CT imaging rather than surface scans. So one of the greatest advantages of 3D surface scans is that they are easy to produce and they are quick to produce. So CT scans typically require a greater amount of post-processing time to clean up that image. It also is necessary to have a radiologist present to help you interpret those images. 3D surface scanners are also a lot cheaper. So in particular, the Next Engine 3D laser scanner, which is what I used for this investigation, starts at about $3,000. So for a forensic anthropology lab, that's much more affordable than a CT scanner, or it's a little bit, it's a better option than trying to get access to a CT scanner, especially if you're not a forensic anthropologist working out of a medical examiner's office. So that was one reason that I wanted to focus on this particular technology, the Next Engine scanner, in this research, is because a lot of forensic anthropologists don't work out of medical examiners' offices and don't have easy access to this medical imaging technology that's either very expensive or that's used in clinical settings, and so is being used for actual patients and not research on skeletal remains. Those are the big advantages.
Okay, for those people who came in late, if you have any questions, go ahead and put them in the chat and we'll get them to Sarah. Sarah, do you have any recommendations for future research for people who are interested in these methods?
Yeah, so this investigation, to my knowledge, is the first to look at morphoscopic traits that pertain to ancestry estimation. So we definitely need to we need to add a little bit more to that literature, do a little bit more research on the morphoscopic traits used for ancestry estimation. More skeletal elements should also be investigated. So a lot of the research that exists on these virtual methods pertains to the os coxa, or the pelvis bones. And those investigations are most frequently looking at age estimation. A little less frequently, they're looking at sex estimation. And again, there is not any literature that I'm aware of that looks at ancestry estimation. So including a larger variety of skeletal elements in our research would be useful. Testing more methods. A lot of the same methods have been tested throughout the literature that exists. So increasing the methods that we look at would help. And once we do that, we can start to modify these methods and make them more useful for assessment of these virtual remains, because all of these methods were created using physical bones. So their application to virtual remains is, through research like this, still being understood. So once we have a better idea of whether and how these methods can be applied to virtual remains, we can begin to make modifications to make them a little bit more effective and informative for use with virtual remains. So definitely there is a lot of opportunity for more research and for future research.
Okay, for everybody who just came in, please use the chat feature to ask your questions, and we'll get them to Sarah for you. Sarah, do you plan to continue with this line of research?
I do. So this is actually kind of a preliminary study, and I'm using this for my master's thesis. So the direction that I plan to take this next is the cranium. So from here, I will look at sex and ancestry traits using the cranium. So again, I'm looking at morphoscopic traits, and I'll see whether or not we can use the cranium, use virtual representations of the cranium to estimate sex and ancestry as a part of the biological profile.
And Sarah, for those who have come in late, can you give us a little bit of a summary about your poster, just for the people who came in late?
Yeah, absolutely. All right, so really quickly, just before launching into my poster presentation, I'll tell you a little bit about forensic anthropology, just in case anyone who is here today isn't super familiar with it. So in a nutshell, forensic anthropology is the identification of skeletonized human remains, and how we go about identifying these remains is by constructing what's called a biological profile. And this biological profile consists of a couple of different parameters, and those include age, sex, ancestry, stature, or living height of the individual, and any individuating characteristics that might help lead to a positive identification. So when I say individuating characteristics, I mean things that are unique to that person. So healed fractures, if you broke your arm when you were a kid, those might be observable in your bones even 10 years later. If you've had any medical interventions, so if you have a screw in your arm from that break, or any type of other medical intervention, we might be able to use those to help identify those remains. So what I did here for this research was I wanted to look at the precision of morphoscopic data from 3D surface scans. So what I did was I took a look at a sample of 50 mandibles from the William M. Bass donated skeletal collection housed here at the University of Tennessee. And I created a I created a 3D surface scan using a next-engine laser scanner for each of these 50 mandibles. And the 7 traits that I looked at are listed down here in figure 1. So when I say morphoscopic traits, I mean traits that we are observing with our eyes rather than measuring with a specialized measuring device. So I looked at height of the coronoid process, shape of the mandibular notch, pinching of the ascending ramus, undulation of the inferior border, protrusion of the mental eminence, gonial eversion, and shape of the inferior border. So I scored all 7 of these traits on those 50 surface scans that I created. And then about a week later, I went back and scored those same 7 traits on the same sample of dry bone. Then what I did was I used Cohen's kappa to take a look at the agreement between the scores that I was obtaining for the virtual remains, or the surface scans, and the dry bones. So the results of that first Cohen's kappa test are indicated in table 2 under that column, the second column entitled kappa value. So 6 out of the 7 traits exhibited significant results and showed pretty fair to substantial agreement. So this last trait does not have a star, meaning that the results were not significant, and indicating that there was poor agreement between those 2 sets of scores. After running this Cohen's kappa test, I ran Spearman's rank correlation coefficient to look at the beyond just the agreement, but how strong the relationship between those scores was. So for the results for Spearman's correlation are in table 3, and pretty similar to those kappa values that we just looked at. All but 1 trait exhibited pretty strong correlation. So after running these 2 tests, I actually went back and scored a subset of those 50 mandibles, of those 50 virtual mandibles. So I took a look at 25 scans and compared those scores to the original scores that I obtained from the virtual mandibles. And to test the agreement between those 2 sets of scores for those virtual remains, I again used Cohen's kappa, and this was to get an idea as to the consistency between my virtual scores. So not only am I scoring physical bones and virtual bones the same way, but am I scoring these virtual remains consistently, or am I getting am I exhibiting decent agreement between the same elements, which indicates consistency. So interestingly, these results, which are listed in table 2 under the rightmost column entitled intra-rater reliability, the 2 traits that exhibited greatest agreement for that first Cohen's kappa test actually exhibited the least agreement. So that was a little bit interesting. And this time, protrusion of mental eminence showed greater agreement. So the results are interesting. They don't necessarily indicate that this is a great method that we should employ right away, but I do think that these results show a little bit of promise for these methods, and continued research might help to tease out which traits are the most might be the most useful when looking at virtual remains, and which we should not look at when using virtual remains, and how we might be able to modify scoring systems when looking at virtual remains. So I have one question here in the chat. So
yeah, for those just entering the presentation, if you have any questions, refer them to the chat window. And the question in the chat is, for the traits that had lower kappa values, what was the directionality of the difference between scan versus actual bone? That is, how did you score differently in person versus using the scan sample? Also, do you think greater experience with the scoring system and or 3D scanning would lead to greater agreement?
So for the first part of that question, how did you score differently in person versus the scanned sample? So the scoring system was the same. I looked at the same traits. I looked at the same character states for each trait. And there was just different agreement between, or there was just different, I observed these traits differently on virtual remains than I did on the physical bones. And for those traits that exhibited the least agreement, pinching of the ascending ramus and protrusion of the mental eminence, so those are actually down here in figure 1. You can see those, and my thoughts here were that those are a little bit more difficult to see, or they are less clear than these traits like gonal eversion that is indicated in this middle image, and shape of the inferior border, which is highlighted in the rightmost image. So those morphoscopic traits, or that the morphology in those regions is a little bit more distinct. So I think that that might be why those are a little bit easier to score on using virtual remains. So for the second part of the question, do I think greater experience with the scoring system or 3D scanning would lead to greater agreement? That's a really great question, and that's actually something that I am going to be looking at as I move forward with this research. I mentioned a little while ago that this research is actually a part of my master's thesis. So next I will also be looking at the cranium, and I'll be looking at Walker's traits for sex estimation and OSA traits for ancestry estimation. And a part of that second half of my thesis, I will include inter-agreement scores, and I'll also be looking at the impact of experience level on how people score these morphoscopic traits. So do professionals or individuals that have been that have been forensic anthropologists for 20 years and that have been working forensic cases and handling remains for all of this time and have so much more experience than I do they score things more consistently than I do? So with greater experience comes greater agreement, or not so much? Is it just difficult to score virtual remains? Another thing that I'm really interested to look at is my personal is agreement in my personal scores for the cranium versus those for the mandible, because the mandible is less frequently used in constructing the biological profile, in estimating sex and estimating ancestry. We might just be less familiar in general with these traits, or because if we kind of reverse that statement, because the cranium is used so frequently for sex and for ancestry estimation, and is routinely cited in forensic anthropology texts, are we a little bit more familiar with those traits and with this element in general, and so we're a little bit more comfortable scoring these morphoscopic traits and therefore seeing greater agreement between these traits? I'm not sure, but that's definitely something that I plan to investigate as I move forward with this research. So thank you for those questions.
Again, if you guys have any questions, go ahead and use the chat feature. And you've touched on this earlier, but for the people who just are just joining us, can you discuss again some of the advantages of 3D surface scans?
Yes. So 3D surface scans are pretty quick to produce. They require pretty short processing time and a short post-processing time. A lot of virtual methods that exist have used CT scans or CT imaging, and post-processing for these CT images can be quite lengthy sometimes. 3D surface scanners, in contrast to CT scanners, are actually a little bit more user-friendly, a little bit easier to operate, and they're kind of associated with a smaller learning curve than our CT scanners. This particular surface scanner, the Next Engine 3D surface scanner, which is what I used here for this investigation, is actually very inexpensive. It's only around $3,000, and when compared with these other top-of-the-line surface scanners or CT scanners, it's very economical and therefore a little bit more accessible to forensic anthropologists that are not working in medical examiners' offices, and so don't have easy access to these medical imaging devices. That's a great question.
Okay, again, for those just joining us, we're joined by Sarah Schwing, the University of Tennessee. If you have any questions, please refer them to the chat feature. We have one question. In your opinion, what is the limitations of the study and any difficulty faced by you while working?
That's a great question. So some of the limitations were, or one of the greatest limitations is just the time that it takes to create surface scans for 50 mandibles. It's that all adds up, and so my sample size for this particular project wasn't great. It's 50 mandibles, which isn't terrible, but more robust sample sizes might help to clear up some of these questions in regards to, okay, which traits are actually useful, which do indicate significance and good agreement. Other limitations of this study, the mandible isn't routinely used in sex or ancestry estimation, so these are just traits that I have been looking at, and I think that because other elements like the cranium are used so much more often, I mentioned this just a few minutes ago, because the cranium is used, routinely used in sex and ancestry estimation, we're a little bit more familiar with this element, and the traits, the morphoscopic traits that we use for the cranium are routinely cited in all kinds of forensic anthropology texts. So these are traits that we are familiar with, that we have read about, that we have seen in textbooks, and that we've been taught in classrooms and have been working with a little bit more. These traits are less, I think, they're much less frequently cited, and so I think they're a little bit less familiar. Given that I have done just a little bit of research with these morphoscopic traits, that I think is a kind of a limitation, but hopefully I will be able to discern whether or not these traits are useful moving forward in my research with the cranium as well.
Okay, again, for those just joining us, if you have any questions, please use the chat feature. And you touched on this before, but for those just joining us, can you talk about any recommendations for future research for people who are interested in these methods?
Yeah, absolutely. So I think that one thing that we can do is kind of increase the methods that we look at in these virtual investigations. So a lot of the long-standing methods that we use for age, sex, and ancestry estimation, the Suki-Brooks method, the Fennis method, ISCON method for various skeletal elements, are the most frequently cited within this virtual anthropology literature. I think that moving forward, if we start to include a couple of other methodologies, in particular the Walker traits for sex estimation from the cranium, OSA traits for ancestry estimation from the cranium, and just more methodologies will help us to discern which might be most useful when looking at virtual remains, and just making this body of literature on these virtual methods a little bit more robust. So just moving forward with this line of research will help us to modify these methods that were originally intended for use on dry bones in a way that makes them more informative and more effective for use with virtual remains. So including more methods and therefore more elements in this research, I think will definitely help us to move forward with these virtual methods.
Okay, for those just joining us, if you have any questions for Sarah, please use the chat feature. And Sarah, do you plan to continue with this line of research?
I do. So I've mentioned a couple of times that I hope to look at the cranium in future research. So I will again be looking at both, looking at morphoscopic traits for both sex and ancestry estimation. So I'll be looking at Walker's cranial traits for sex estimation and the OSA morphoscopic traits for ancestry estimation. And I'll be including in this kind of second half of my research a greater investigation of inter-observer agreement, as well as the impact of experience level on scoring. So do individuals with greater experience, those who have been forensic anthropologists for 20 years, are their scores more consistent, or is it more that these virtual methods are not as effective as using dry bone? So a couple of times I've actually talked about some of the future directions for this research and recommendations that I might give to individuals who are interested in these virtual methods. So one big thing is that these methods are not standardized. So use of 3D surface scans is not a standardized method. And when I say that, I mean that you can generate these 3D surface scans in many different ways. So you can, there are all of these different settings that you use when you construct these virtual images or these virtual models. And there is no tried and true method or published method of doing this that is done the same way every single time. So this is a really great area for future research, is trying to standardize these methods, and also taking a look at not only next engine surface scanners, but taking a look at other surface scanners as well. Is there a large difference between the scans that are produced by 3D surface scanners or by next engine 3D surface scanners and by other more high-end surface scanners, or are they kind of creating very similar images, and thus we are observing morphoscopic traits in really similar ways between the scans that are generated from these different scanners. And if we're scoring these scans in really similar ways, meaning that the next engine scanner is pretty much good enough, then again, we need to begin to kind of standardize the parameters that we use for, or that we set for constructing these virtual models using the next engine scanner, just so that we're all collecting these virtual, or creating these virtual remains in the same way.
Sarah, for those who have just entered the discussion, can you just give us a brief overview of your poster?
Yeah, of course. So really quickly, I'll talk about what forensic anthropology is, just for those who aren't familiar with it. So in a nutshell, forensic anthropology is the identification of skeletonized human remains. And the way that forensic anthropologists go about identifying these skeletonized remains is by creating a biological profile or estimating a series of biological parameters for these remains. And those parameters are sex, age, ancestry, stature, and any individuating characteristics. And when I say individuating characteristics, I mean like healed fractures, any sorts of medical interventions, so a hip replacement, what have you, that might help lead to a positive identification of this individual. So typically, skeletal remains are assessed in person. We use dry bones to create this biological profile to estimate age, sex, ancestry, stature, etc. But over the past couple of decades, there has been increased interest in these virtual methods. So what I did for this research was look at the precision of morphoscopic data from 3D surface scans. And when I say morphoscopic data, I mean, or morphoscopic traits, I mean traits that we are kind of measuring with our eyes rather than with a specialized measuring device. So I looked at a sample of 50 mandibles, 50 dry mandibles from the William M. Bass donated skeletal collection housed here at the University of Tennessee. Using a next engine laser scanner, I created 3D surface scans of each of these mandibles. These morphoscopic traits are all listed down here in figure 1. And those are height of the coronoid process, shape of the mandibular notch, pinching of ascending ramus, undulation of the inferior border, protrusion of the mental eminence, gonial eversion, and shape of the inferior border. So what I first did was score each of these 7 traits on these 3D surface scans, and then about a week later went back and scored this same sample of 50 mandibles in person, or I scored the dry bones, but assessed the same morphoscopic traits. Then I wanted to compare both sets of scores, those that I obtained from the dry bone and those for the virtual remains, to see how well my scores agreed with one another. So to look at this agreement, I used Cohen's kappa, and the results of this test can be seen in the second column in table 2, entitled kappa value. So for 6 of the 7 traits, I saw fair to substantial agreement and significant results, which seemed pretty promising. After looking at the agreement or using Cohen's kappa, I wanted to look at the strength of the relationship between these scores. And so I used Spearman's rank correlation coefficient. And these results can be seen in table 3. So similar to the results obtained for the Cohen's kappa test that I just mentioned, the results for the Spearman's correlation were significant for all but one trait. And again, that trait is protrusion of the mental eminence. So after I ran Spearman's rank correlation, I went back and scored a subsample of those original 50 mandibles, but focused on 3D surface scans. And what I did was compare the scores from my first trial of scoring those virtual mandibles to that second trial of scoring those virtual mandibles. So again, for this test of kind of intra-rater agreement or intra-rater reliability, I used Cohen's kappa. And interestingly, the results that I saw for this second Cohen's kappa test were a little bit different than what I saw for the first. So shape of the inferior border and gonal eversion were the 2 traits that exhibited the greatest agreement in that first Cohen's kappa test. But these were the 2 traits that exhibited the least agreement for this test of intra-rater reliability, just between my scores of virtual mandibles. So that was an interesting finding. So moving forward, I would like to also look at my scoring consistency of dry mandibles. So am I seeing similar patterns in the way that I score dry mandibles? Were there just a couple of odd mandibles in the mix that lowered my agreement scores? And I'd also like to increase sample sizes in the future to kind of get a better idea as to some of the results that we're seeing here. So it seems that protrusion of the mental eminence is not the best trait to score from virtual remains, but shape of the inferior border and gonal eversion, as well as undulation of the inferior border, they appear to be reliable using virtual remains. So if I take a look at a greater sample, will I continue to see good agreement between dry scores and virtual scores, or not so much? But I do think that these results show a little bit of promise for moving forward with these virtual methods.
Okay, I just want to remind everyone we have about 15 minutes left in today's poster session. Please remember you can still leave your questions in the chat, and we'll have them available in written format shortly. Sarah, for people just entering the discussion, can you talk about any recommendations for future research for people who are interested in these methods?
Yeah. So a lot of the virtual investigations that exist have looked at CT scans. So more research on these methods, on virtual methods using surface scans, will definitely help us to learn more about the utility of surface scans in constructing the biological profile. Are the surface scans generated by these by the next engine surface scanner in particular, useful, or do we need to use higher end surface scanners, or are surface scanners not providing us the information that medical imaging technology like CT scanners are, and so we should stick with those CT scans. I think another opportunity for future research is to look at more methods. So moving forward, I would like to look at the cranium, and particularly Walker's morphoscopic traits for sex estimation and the OSA morphoscopic traits for ancestry estimation. So just including more methods in future research will help us to get a better idea as to which methods are useful, and specifically which traits are the most useful, and how we can begin to modify these methods. A lot of the research on these virtual methods has looked at the Suchi-Brooks traits, as well as the Fennis traits. So kind of expanding our focus on other skeletal elements and other age, sex, or ancestry estimation techniques will help us to learn which methods are most useful, and will help us to learn how we can modify these methods to make them more informative and effective for use with virtual remains. Also, through continuing research, if we are seeing that the next engine scanner is a good way of assessing virtual remains, we need to start to standardize the parameters that we use for model construction, so that we are all creating these scans in the same way, and so that we can adhere to those Daubert guidelines, and this can be an admissible method in a court of law.
Okay, we have some new participants. If you have any questions, please refer to the chat, and we'll pass them along to Sarah. Sarah, again, for the people who just now arrived, can you talk about some of the advantages of 3D surface scans?
Of course. So 3D surface scans are pretty quick to produce. They have a slightly longer generation time, but a quicker post-processing time than other 3D image construction technologies like CT scans. The learning curve for surface scanners is also quite a bit smaller than that for CT scanners. So they're a little bit more user-friendly. Surface scanners, particularly the Next Engine 3D laser scanner that I used for this research, are also cheaper than CT scanners. And for forensic anthropologists that are working outside of medical examiners' offices and that don't have easy access to this medical imaging equipment, this is a great option because the scanner is affordable and is a desktop scanner, so it doesn't require a lot of floor space. It is easy to set up, easy to take down, and provides really great images that are manipulable, if you will. So similar to how I might look at a physical bone, I can manipulate these 3D surface scans on the computer in front of me. So I can rotate the object to look at different sides and get a different view of whatever morphoscopic trait I might be looking at. Some scanners in the Next Engine laser scanner is one of these, will also preserve the color of the bone or the texture of the bone, which might be useful in some instances to help you distinguish defect from not defect. But the largest advantages, I think, are the accessibility of the Next Engine laser scanner, because it's cheaper and just a better option for those without ready access to these medical imaging devices like CT scanners.
Okay, we're coming up on the end of our session, and just want to thank everybody for stopping by. And if you have any last-minute questions, just go ahead and put them in the chat before you return to the main webinar. Sarah, is there anything that you want to say before we close out? Anything you want to add to your presentation?
I don't think so. Thanks everyone for coming and joining me and listening to my presentation today. I can also go ahead and provide my email address in the chat, so if anyone has any questions or is interested in this research, please feel free to contact me.
And Sarah, do you plan to continue with this line of research?
I do. Moving forward, I'm actually going to look at the cranium and look at Walker's cranial traits, morphoscopic traits for sex estimation, and OSA traits for ancestry estimation. This will kind of be the second phase of my master's thesis. So my research here on the mandible is kind of the first half. And from here, I will look at the cranium and see if these methods, these different types of morphoscopic traits, Walker's, and OSA traits are useful for helping to construct that biological profile from the cranium.
We have one last minute question. Can you briefly touch on ancestry again?
Sure. Okay. So ancestry estimation we're looking at, we typically distinguish between a couple of broad groups. And these are individuals of African ancestry, of European ancestry, of East Asian ancestry. And as we continue to increase our skeletal sample sizes from other regions, we can begin to estimate ancestry more specifically. So we can begin to narrow down these groups. And so we can begin to include just smaller categories rather than these broad European or Caucasian categories. So it's important to distinguish between ancestry and race because race is a socially constructed concept, and so that's not what we're doing here. Here we're trying to estimate more the origin of that ancestral population. So the traits that I looked at that pertain to ancestry estimation here are, actually I've looked at all of these traits in and their utility in ancestry estimation. Those that are more frequently used for sex estimation are going to be gonial eversion, so that's the trait outlined in the middle image. Shape of the inferior border, so that's going to be the trait depicted in the rightmost image in figure 1. Undulation, as well as protrusion of the mental eminence, which are the kind of lime green and yellow highlighted traits in that leftmost image. Those are fairly frequently cited, as well as pinching of the ascending ramus, which is highlighted in that bright blue color. Those three are cited more frequently in ancestry estimation. The two traits indicated in pink and red, those were traits that I included in a personal research project a couple of years ago. And so those are not well represented in the ancestry literature, but they were differences that I was seeing in my sample, and so I included them and decided to move forward with these traits in this research as well.
We do have one last question. are you using discrete measurements or more continuous data when combining features to come to a conclusion?
So no worries. So the traits that I looked at are actually, I scored them ordinally. So it's kind of between discrete and continuous. So each 6 of these 7 traits all had 3 different character states associated with them, meaning that each trait could be classified as one of 3 different kind of forms, if you will. So for, let's take shape of the inferior border, for example, highlighted in dark green in that rightmost image. So that character or the trait is shape of the inferior border, but the character state or the type of kind of the form that trait takes would be either square or binary, or I'm sorry, bilobate, would be round or could be pointed. So each of these traits, except for one, had 3 different character states associated, and one trait had only 2, and so that was a discrete or binary trait. And then there weren't any continuous traits that I included here. That's a good question.
Okay, so our time's up. If you came late, this presentation will be available on the GFJC YouTube page. If you have any last minute questions, go ahead and put them in the chat window. We'll provide answers in written format shortly. I want to thank everybody for stopping by. And thank you, Sarah. You did a great job.
Thank you.
And everybody have a good day.